All right, so let's start. So here, this looks about where we're starting. So let me just show you the notes. Let me just get you caught back up kind of real quick intellectually where we're at. So we were looking at straight line solutions. And so given this, we're making the guess of e to the lambda t where lambda vector, right? We're going to guess this is our solution. If we make this guess and plug it through, we find out it works, right? We find out it works. And then and so if we plug this in here, and do a little algebra, we get that this equals this, and so it's a solution, right? So it solves the differential system. And so we're going to use our linear algebra. This is just a quick review of linear algebra. Remember we want our matrix to act like a single scalar. And so to find that, we're going to find a scalar and a lambda such that this works for. Well, how do we find that? Well, we just solve this equation. And we'll be doing a lot of eigenvalues and eigenvectors really soon. Okay, so we're going to solve this. I will teaching you how to, do this, just an easy way to find that. And so let's start with our first example here. So our first example here, is one where I do not have the answer in front of me. That is fine. I can figure it out. All right, so let's do this.
Did you want to skip example 17?
Did we not do 17?
Yeah, we're on page 10, example 17.
Or on. Hey. I'm on page 11, ain't I? Whoop, whoop. So let's do page 9. I'm like, gee, this isn't what I wanted to do. All right, so we're going to do this, right? We're going to do this one the long way, right? That way I'm going to show you all the steps in pedantic detail so you don't get lost. And then we'll shorten it, okay? Okay, so let's do this. So what do we first thing we want to do? So in here, we want to guess that E to lambda t v lambda, and we want to find two of these, right? That's our guess. Well, what's the first thing we want to do? We need to find lambda. We need to find lambda, and we need to find its corresponding eigenvector. So we need to find its value in the vector. All right. And so in order to make this guess, let's convert this into a system. So here we're going to say dy dt is equal to 2, 2, 1, 3 y. And this is what we set up before. We're going to find the eigenvalues, and we're going to find the eigenvalues and eigenvectors for the system. So how are we going to do that? Let's first find the eigenvalues. So the eigenvalues here are found by taking the determinant of a minus I lambda, and we set that equal to 0. And so that in this case would be 2 minus lambda, 2, 1, 3 minus lambda equal to 0. All right. This implies that 0 equals 2 minus lambda times 3 minus lambda minus 2. Okay? And there we go. And so this is equal to lambda squared minus 5 lambda, if you multiply it all out, plus 4. And if I factor that, that'd be lambda plus lambda minus 1, lambda minus 2, or lambda minus 4, sorry. Yes. So that implies our lambdas here are lambda is equal to 1 and equal to lambda 2 is equal to 4. All right, so I'm going to find the eigenvectors. So here'd be, if I was writing step 1, put it in matrix form. Step 2, find the vector. Step 3, or find the values. Step 2, find the vectors. Hold on 1 second. 1 second. Come on, you. I keep the door shut. So it's quiet, and guess what? Was Cam sitting there whining? He's like, I want in. There you go, little basset hound. Let me go back to teaching. All right, so here we're going to find this. So let's start with lambda equal to 1. So lambda equal to 1 is going to be our lambda 1. We'll make this our lambda 2. All right. Hey, don't make a noise. I let you in and you cause havoc. This is what I get. So what do we have here? So we want to solve this equation, and I'm going to show you how to solve it a different way. And the reason I'm going to show you how to do it this way, that way when we go to complex, it won't be as egregious to you. So here, I want to find the eigenvector. And so I'm going to set it up this way. It's where we're multiplying by the matrix is equal to multiplying by the eigenvalue. So what have I set up here? Hold on, let me write exactly what I set up here. I set up here is a eigenvector is equal to eigenvector, right? That's what I'm solving for this. I want to solve for a vector in which this is the case. And the vector here for lambda 1 will be given by x1, y1. And then for lambda 2, it'll be x2, lambda 2. All right, so I'm going to solve this. All right, so this translates into, if I move everything over all to one side, I'll have 1x1, because I minus this over, plus 2y1 equal to 0. And here I'll have 1x1 plus 2y1 is equal to 0. Are these the same equation? Yes, and so we can cross one out, right? So if it's this, if you've found the correct eigenvalue, when you solve for this, one of these equations will be the same. Now, is this the way I taught you how to do it last time? No, I want to show you a different way. That way you can find out which way works best for you and choose between them. Okay. All right. So this is the only equation. As long as I satisfy this equation, I by definition satisfy this equation. They're the same, right? And so here I have x1 equals, and I'm gonna put a 1 in front of it, equals to minus 2y1. Okay. And so how do I choose? Now this will have an infinite number of solutions, right? If I choose x1, I can solve for y2. If I choose y2, I can solve for x1. What I almost always do in this case is I choose x1 to be the coefficient on y2. And then I choose y1 to be the coefficient on x1. And the reason I do this is A, I don't have to think about it, and B, it automatically solves it, right? Because then by definition, this will be y1, x1, and this will be x1, y1, right? And so notice here, if I plug in -2, 1 into this equation, I solve it. This also satisfies this equation, which also satisfies this equation. All right, now that we have this, we have our first one. So let's do this again. So we're going to do this one more time. So we're going to find lambda 2, or find v lambda 2, sorry, v lambda 2, where lambda 2 is equal to 4. All right, so here we have 2x1 plus x2 in this case, 2y2 equals to 4x2, and then we have x2 plus 3y2 equals to 4 times y, little y, 2. This translates, once we move it all over, I'll have minus 2x2 plus 2y2 equal to 0. And then here I'll have x2 minus y2 equal to 0. Are these two equations the same? And the answer is yes, right? I multiply this equation by -2, I get this equation, right? And so we'll go ahead and cross one off. And this time I'm going to cross off the top one. So the same cross, so same cross off. Now why would I cross off the top one? Well, the top one's more complicated than the bottom one. That's all. So this implies that x2 equals y2. And so for b lambda, make that look like a b lambda 2, I'm just going to choose the coefficients here. But here the coefficients are 1 and 1. So here I have 1 and 1. So here I have my vector, 1, 1, and this. Now from our theorem, from our cute little theorem, for our answer, right, we have a solution. We have y of t equals k1 e to the lambda 1 t. So here's our theorem. B lambda 1 plus k2 e to the lambda 2t e lambda 2. And so for us, that's going to be y of t is equal to k1 e to the t minus 2, 1 plus k2 e to the 4t 1 and 1. And there's our solution. All right. So let's do, let me leave that up for a second. Did you guys copy? No, didn't bring. So this is the first complicated one we solved start to finish, right? And we're going to do the same method. We're going to do the same method for the rest of the course, or for the rest of the chapter, right? We're going to put in an we're going to make a matrix, we're going to find eigenvalues and eigenvectors, and just put it together. Now, this part you should be comfortable with. You should know how to do this for normal numbers. We'll touch on complex numbers. You should be comfortable for real numbers and repeated numbers, but for complex numbers, we'll touch on that. So let's go to the next one.
Hey, quick question. Sorry to interrupt.
Yeah, go for it.
For the second term on that y of t, should it be k2 e to the 4t?
Oh,
Or
yes.
should it just be e to the 4? Okay.
Thank you.
Mhm.
You're very correct. Thank you. If I make mistakes, please let me know and I will fix them. All right, so now let's look at this one. Let's look at this one. Let's kind of do, so let's find the straight line solution for this. Well, do we need to do the method we did before? No, but because we solved this one, I think 3 times now. Let's do it the 4th time with the new method, right? dy dt, and here I'm going to do it a little bit faster. So here we'll have step 1 equals 2. In this case, it'll be 2, 3, 0. Notice there's no x term here, minus 4. Here, and lambda 1 is equal to 2, and lambda 2 is equal to minus 4. Now, why can I just state that, right? Why don't I have to solve anything? Why can I just state that? And the reason I can just state that is this is upper triangular. Therefore, the eigenvalues are just the diagonals. Okay? So here we go. So I'm going to state this. So that's kind of step 2. If not, punch it through a calculator. All right, so here we want to find b lambda 1. All right, so let's find b lambda 1. I want to make sure I am doing this. All right, so b lambda 1. Where lambda 1 is equal to 2. So what do we have here? In this case, we have 2 of x1 plus 3 y1 is equal to 2 x1. And then here we'll have My brain will fire. 0, x1, minus 4, y1 is equal to 2, y1. Do these two basically say the same thing? And the answer is yes, because if I move this over, I get a 0. So this is basically saying this says something, this says something. But what does this say? Just for sake, just since this one's complicated, I'll actually show the step. This is 3y1 equals 0, and this is minus 2y1 equal to 0, right? Are these the same thing? Yes. What is this saying? This just says y1 equals to 0. So what's my vector? Well, if my vector is y1 equals to 0, I'm just going to put in a 0 here, and I can put anything I want up here. This could be pi, it could be the square root of 7. I'm going to put 1. Make my life easy, right? So if you get one of the variables is 0 by definition, that means the other one's free, and just make it a 1. Okay? All right, lambda, v lambda 2. V lambda 2, where lambda 2 is equal to, in this case, -4, be 2x1 minus 3y1 equals 4. These should be 2s. I'm on lambda 2 minus 4. And then here we'll have 0, x2 minus 4, lambda 2 equals minus 4, y2. Now notice in this case, I can safely cross this one off since this provides 0 information. What does this end up saying? This ends up saying 0 equals 0. Well, that doesn't tell me anything, right? So I'm only left with what's up top. And what left up top is minus 2x2 equals minus 2x2 minus 3y2. Oops, this should be a plus. Boop, boop, equals to 0. Go ahead and translate that over. And so that means, and I'm going to just, for ease, I'm going to move over the x2. This way I have it, things to be positive. So v lambda 2 is equal to what? Here, I'm going to choose x2.
Why was it up minus 2x? Sorry. You add the 4x to the other side, you get 6x.
100% correct. Thank you. Whoops. Back it up. Back it up. This is why you always do. Like I said, I don't have this one in front of me, as I should. What am I worried about when I'm thinking this? Not the problem. It's like, am I explaining this in such a way that I'm not losing everybody? Ta-da! So what happens here? What's the eigenvector here? Go ahead and write it out. I'll let you guys solve it from here. What's the eigenvector real quick? 3, 6. Okay. So I see a bunch of 3, 6, -3, and 6. So yeah, -3 and 6, that's fine. So you can have this as -3 and 6. I would probably simplify that just to be -1, 2. In fact, I'd probably move the negative down below because I like to have. Now notice, is this fine and this fine? Sure, they're both equally fine. What's going to happen, what will change here, so I'm going to write out the solution real quick, is k1 e to the lambda 1, which in this case is 2t 1, 0, plus k2 e to the lambda of 4 minus 4t. And if I put in -3, 6, basically what happens here is that when I solve for k2, I'll get a different k2 than if I put in 1, -2, right? In fact, the difference between that k2 would be a -3, right? This one, if I took whatever K2 I solved for this one, multiply -3, I'll get whatever K2 I did for solve this one. So this constant allows this to be any vector which satisfies the equation. Okay? Which satisfies the equation. All right, so here's someone asked a question. In the discussion of these problems, it seemed easier if we could just use rough round to find line and eigenvectors. Yes, so for these problems, I want you to show the work of finding the eigenvalues and eigenvectors. I'm going to declare that finding the eigenvalues and eigenvectors is part of the problem. Okay. Some problems I declare it's not, some parts of this. For this point, I'm going to declare it is part of the problem because I want you to have more practice doing it by hand. Now, don't get me wrong, if you're taking the exam, by all means, check it in Wolfram Alpha, right? By all means, do check the answer. Okay? All right, let's do one more. Let's do one more of these, and then I think I get into yes. All right, so let's do this even faster. So let me show. I'm not horribly particular on the notation, and so here let me just. So here you can just write A as this, as long as you state A in either this form or this form, I'm okay, right? And so here I can just say A is this, and then I can say, you know, find my eigenvalues, right? So find the lambdas. So find lambda, in this case, it would be -4 minus lambda, 1, 2, -3 minus lambda. For your homework, you're going to have a 3x3 case. For the 3x3 case, it just says use the computer algebra system. That's literally what it tells you to do, right? In that case, I've given you permission to find the eigenvalues and the eigenvectors using Wolfram. That makes sense because I specifically say 7 and 9 use the CAS, right? All right. I set this equal to 0. What does this end up being? This is 4 minus lambda. Oops. -4 minus lambda times -3 minus lambda. So this minus that equals to 2. You solve this out. I'll get lambda 1 equal to -5. I'll get lambda 2 equal to -2. All right. So if lambda 1 is equal to -5, I am going to have the following equations. I'll have -4x1 plus y1 equals to -5x2. Oops, 1. Sorry, there's a 1. The other one is positive 2x1 minus 3y1 equals -5y2. Are these two the same? If I move this over, I'm going to get x1 plus x2, right? Or x1 plus y1 equals 0. If I move this over, I'm going to have 2x1 plus 2x2 equal to 0. And so here, go ahead and just mentally check it. So go ahead and mentally check it. Check it in your hand. You don't have to physically show me these. Just mentally check it and then cross off. I'm going to slowly remove parts of what I mandatory want to see until I get it kind to a bare bones system for you. And so here this will equals -x1. -x1 equals y1, and therefore my vector here is 1, -1. Okay. Let's do lambda 2 equal to -2. Oops, that's a negative there. I'm going to have to save some room. Let me save some room for the answer. So I'm going to put this up over here a little bit. So I'll have -4x2 minus or plus y2 equals -2x2, and then I'll have 2x2 minus 3y2 equals -2y2. If I move this over, what do I get? I'll get -2x2 plus y2. If I move this over, I'll get positive 2 minus y2. These are essentially the same. Cross it off. This implies what? Well, that just implies that y2 equals 2x2. And so my vector here is the following. 1, 2. All right, then I can write out my solution. So here we have y of t equals k1 e to the minus 5 t 1 minus 1 plus k2 e to the minus 2 t 1 2. Okay, so you kind of get the song and dance of how to do this. We've done a bunch of these. We already covered the site. All right, so let me leave this up for a second so you can copy. Oops, let me zoom out. And then we'll talk about how to draw these things. All right, let's talk about drawing. Oops, I forgot something here. That should have a little, this should read y2 less than 0 less than lambda 1. Okay, so how to draw the phase planes for when lambda 1 does not equal lambda 2. And real. Let me write and real. These need to be real. So you're going to draw on your straight, whoops. These, you're going to try v lambda 1 and v lambda 2 to the origin. So you're going to draw your two straight line solutions. If the lambda is negative, we're going to draw it inward, and if lambda is in, we're going to draw it out. If the lambda is negative, you can draw the arrows pointing inward, and we're going to draw it pointing outwards, and then sketch the rest lines based on that. So let me kind of show you how this goes down. Okay. Yeah, so let me show you. So what we could have here is we could have our v lambda 1. Let me start with the source. Let me do this in reverse order. So here, let's pretend we have like one that's going this way. All right, so here we have v lambda 1. Yeah. And it points this way. And since it's positive, we're just pointing out. And so then I'm just going to make a straight line that goes all the way through it. So this will point out, this will point out. Okay. Then I'm going to draw in v lambda 2 and just pretend for a second it's this way, right? This is v lambda 2. The vector, if I drew it in space, would be this way. I'm going to go ahead and draw it all the way out. I'm just going to write v lambda 2. This one's going out and this one's going out. And so if you draw this, we'll actually do this for real situations. Once we draw this, then the rest of it, and notice here that v lambda 1 is stronger, right? So this is the higher value. So it'll kind of come up and swoop in this way. And this will make a lot more sense after we draw a couple real ones, but I do want to have this in your head. So you'll start here and you'll kind of curve towards the line. And let me explain why. Let me go back to a real solution here. Let me do the sync. That way we can do a real solution. Okay. So let's do the same thing here, but this time we're going to just make it a sync. I'm going to draw it in basically the same. Oops. These should always go through the origin. 0, 0 is a solution to this. Except these are going to go in. And these will come in and come in like so. If it doesn't make perfect sense right away, don't worry about it. We'll go ahead and we'll actually draw real examples, and then it should make more and more sense. Let's look at this. Let's look at this answer real quick. Let's look at our answer right here. And let's see if I can this answer. Okay. Notice here, if I have k2 equal to be 0, right, and all my solutions in this line, that's what we call it, a straight line solution. As t gets larger, e to the negative 5t gets smaller and smaller. And so this will go slowly into 0, right? If all my solutions in this one, as t gets smaller, it slowly goes into 0. But if I have a mixture of these two solutions, notice that e to the negative 5t gets smaller faster than e to the negative 2t, and that's why it has some curvature to it. Okay? We'll do some real solutions that will make a lot more sense when we do these. I just want to give you the brief sketch. So here, if it's, you draw the two straight line solutions, and then you'll have, and they'll follow, and then you kind of, they'll point in, and then you just kind of draw the rest of the lines. If it's a saddle, and I'm going to just do this more of an X for the saddle. If it's a saddle, so if I have one pointing out and the other one pointing in, so one straight solution, so one negative, one positive, the other solutions just kind of go in and go out and kind of follow the saddle. So just kind of like this. And then the arrows go this way for that one, and the arrows go this way for that one. So let's do this. All right, how do we solve this one? I think we already did today, didn't we? Yes, yes we did, right? Here's our solution, right? So I want us to find the general solution and do this. Did we solve this already? Yes, it is right here. So let's go ahead and copy that over. So the solution to this, so solve previously. In fact, let's say solved in 17, right? Is that what this one is? Yep, solved in 17. So that's not how you spell solved. Solved in 17 to be k1 e to the t2 minus 1. Is that what we had? I want to keep it the same as we had before. No. This one is minus 2, 1 plus k2 e to 4t1 and 1. So here we just solve it like we did before. Now we just want to sketch the phase plane. So let's do this. All right. Let's just start with this one. So I'm going to go 1 in the x direction, and then 1, 2 in the y direction, and I get some point that looks like this. And I know I'm going through the middle point. And just to make my life easier, let's do a positive 1. Nope, I did that backwards. All right. I'm going minus 2 in the x direction and positive 1 in the y direction, right? Don't mind my dyslexia. Or I can go negative 2 in the x direction, or I can go minus 2 in the x, or positive 2 in the x and negative 1 in the y. And so here I have the solution right here, or the set of solutions. So in this case, you can imagine at this point, k1 is equal to 1. And I start at this point, and what am I going to do? So since t is positive, this is just going to slowly go more and more out, right? And here, if I had k1 to be negative 1 and k2 to be 0, right, which is this point right here, what happens as I go forward in time? It's going to go more and more out. And so my solution in isolation, let me just draw it in purple real quick. So let's pretend I had k1 equal to minus 1 and k2 equal to 0. And remember, we can solve for k1 and k2 using our initial values, right? In that case, my point would start here and go this way, right? And that would be my solution, right? That would be the solution to this, right? In fact, I'll leave that. I was going to erase it, but I'll go ahead and leave it. And so this just represents a whole bunch of solutions. So let's do another solution. Let's do another front. Let me do it in blue. So here we have 1 and 1. So 1 and 1 would be here, and then this will just kind of go exactly even this way, right? And let's pretend we have another solution here. Let's pretend I had k2 equal to 5 and k1 equal to 0. Well, in that case, I'd be over at 1, 2, 3, 4, 5. And what's going to happen here? Well, I have positive, right? This is positive, and so this is going to shoot out this way. And so here we have, so the phase portrait or the phase plane, right, represents all the answers, right? So given any initial condition, if I know where I'm starting, I can figure out what's going on. Now, once I have these two, which one of these is the stronger line? Which one is stronger? Well, we look at this. We look right here at e to the t, right? And then have e to the 4t. Which one of these two is going to grow faster? This, right? This one's going to grow faster, by a factor of 4. And so here, when I kind of sketch in the other line, it's going to come out and go forward and shoot out this way. And come out and go forward and shoot out this way. And come out, go forward, shoot out this way. And the same thing with these. If I started on this side, they'll come out and come this way. Okay. All right. Now, so that's how we draw this one. But let me show you how to do it in the computer. All right. What am I looking for? This class, my little program. I also can explain the project right now. It's actually almost a perfect time to explain the project. Maybe explain the project in 2 more minutes. All right, so here I have this cute little program, and it's going to give me linear phase portraits, right? Anyways, so let's go ahead and clear. All right, so let's just type this in. So here, let's go back. Hold on. And browse all tools. Whoop. Let me whoop. You can use the system solver, but we don't need that. We're just going to use linear phase portraits. That's what I'm going to use to do that. Well, however you want to do this, there's 1,000 ways. Not picky, but I do want you to use a computer. This one's really easy. I'm just going to type in 2, 2, 1, 3. And here, if I type in the eigenlines, bam, those are my eigenlines, right? And now, if I click on points, I can see that this matches my graph exactly. And so here's just nothing more than a vector field, right? Or a directional field. We learned how to draw these, right? And so here, does this match what we have here? Yeah, very, very closely, right? And so this is just a way of kind of saying this is how the directional field looks. Okay. And so given any, so let me clear it real quick. So let's pretend I started here. These are my initial conditions. Boop. There we go, right? And here's my initial, boop, there we go. And so you can see that it just progresses in such a way. And so just so the program makes nice little lines, it's actually drawing lines forward and backwards, right? And so that's how you do that. So let's do another one. I'll go ahead and export these. Export as PNG. Yep. Current class, good notes. Save. File. Export. Current class, completed notes. Save. File. Export. Current class, completed notes. Save. That way I have them if you guys want them. And let's do a couple more of these. All right, we're on page 13 now. If I had a better computer, I could save more space, but I don't, and this thing gets crunchy. All right, I'll open up Photoshop. All right, we're on 13. Let me open up 13 and 14. 14. I bet we can get these two done. All right, so 13. Let's go ahead and do this. And boop, boop, boop. All right. So we want to find the general solution and sketch the baseline for these puppies. So let's do it. All right. Making a decision. All right, so so here, if we write this is dy dt is equal to 2 minus 1, 4 minus 3, right? All right, which implies, so when we want to find lambdas, we're going to take, oops, do not do that. Give me back my blue. So to find the lambdas, we're going to just take lambda 2 minus lambda minus 1, 4 minus 3 minus lambda. And this is going to equal lambda 1 equals to 1, and lambda 2 is equal to minus 0. And that's going to imply, so I'm skipping steps. So I'm skipping steps here, just because I want to get to the drawing. But do show all your other steps beforehand. Okay. I'm not positive how I set up because we solved it, and then we draw it. I don't remember if I teach you how to draw it and then we solve it, or we do the other way around. I don't remember. We'll find out. Anyway, so v lambda 1 in this case is 1 and 1, and v lambda 2, if not I'll be v lambda 2 to this one is 1 and 4. All right, so let's sketch this real quick. Let's do the best we can. Oops, let me actually write in the solution. Let me put my solution down at the bottom. So my general solution here is k e to the t1 1 plus k2 e to the minus 2t1 4. Okay. So the first two solutions we draw. So remember this base plane, what we're drawing here is the set of all solutions based on for this equation. It's a representation of all the solutions. Remember, one solution is just going to kind of go forward and just follow the arrows. But we're going to draw all the solutions so that way you have a concept of where you start is what's going to happen to it. So we're going to start with this one. We're going to start with this straight line solution. So this solution is in this direction, 1 and 1, right? And so we just go ahead and draw that in. I missed terribly. Still missing. Still missing. There we go. Oops, no, put that back. If anyone ever seen people draw digitally, they do that sometimes, especially not very good. They draw. Nope, don't like that. They don't. Okay, that line looks good. All right, what about this line? So notice here that this is positive. And so since it's positive, I'm going to put outward pointing arrows on it. So this one, the arrows are going outward. Why is that? Because as time moves forward, the solution is going to push outward because this number is going to get larger and larger and larger. Here, let's do 1 and 4. So it'll be 1 and 4. And here, our eigenvalue is negative, and so this one's going to go in. Okay. And so here you draw one solution, you draw the second straight line solution, and then based off of what you have, you draw in the rest of it. And so in this case, we have a saddle here, so it's going to come in, come back out, and the direction here is this. This is going to come in, come back out. Direction is this, and so it's just going to follow the arrows here, and then here this is going to come in, come out, come in, and come out. And then here it's going to come in, come out, and come in, and come out. Okay, so you just kind of make swoops in between. Now let's graph this digitally. Where's my digital one? Whoop. Let's do this digitally. All right, what do I have here? I have 2 minus 1. I'll let you guys draw that as I'm typing this in here. 4 and then minus 3. Ta-da! All right, and so here we have our thing, and so here we have our. We'll go like this. Da, 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 da. And notice how ours looks a lot like this, right? Looks a whole bunch like this. Maybe ours kind of scooted in more than it should, right? That's okay. And so this is a really easy way to do this. Now, the reason I have you drawn by hand is that way if you look at a solution like this, if you look at the solution here like this, I gotta remember you guys can't see what I'm touching. You should be able to picture the phase portrait in your head. And if I don't have you drawn by hand, you won't be able to picture it in your head. All right, let's do this one. How much time? We got lots of time. Did we do this one? No, we haven't done this one. All right, let's just crunch through this one. All right, so let's crunch through this one. All right, so here we're going to have dt. I'm going to skip steps again because the point of these problems is the drawing. And I think you can figure out how to find the eigenvalues and eigenvectors at this point. I might be crazy, but minus 3. All right, so we're going to find the eigenvalues. So we're going to find the lambda. So the lambdas here are found by taking -1 minus lambda, minus 2, minus 1, minus 3, minus lambda. Set that equal to 0. Once we do that, I'm going to get lambda 1 is equal to minus 4, and the eigenvalue associated with that will be 1 and 1. Minus 1, and the eigenvalue associated with that is minus 2, 1. Okay, and so what's our solution? Our solution here is y of t equals to k1 e to the minus 4t 1, 1 plus k2 e to the minus t minus 2, 1. All right, so let's go ahead and draw that in. All right, so here we have this one at 1 and 1. Total missed. Oop. I got rid of too much. No. Might be that way. There we go. And this is at minus 2, 1, so something kind of like that. That's good enough, right? All right. This one, on the 1 and 1, 1, it's going in, right? And then here, this one's also going in. All right, but notice here that this one here is stronger. This one here is stronger. And so which way are the swoops going to do? The swoops are going to be more parallel to the stronger line. So I'm going to write that. The swoops, that's a technical term, are more parallel to the line of the more the greater absolute value of lambda. Okay, so for a positive would be the more positive one, for the negative one would be the more negative one. And in this case, and if there are different signs, it doesn't matter, right? I mean, it kind of does, but it doesn't. So in this case, they're going to be more parallel to this line. What does that mean? They're going to look more like this, right? And so they're going to come in, and so the lines are going to start more parallel to that. Does that make sense? Whatever one is stronger, the lines are more parallel to. Maybe. All right, I'll let you draw this. And then I will type it into our happy little program.
I do have a question with the strength.
Yes.
With the saddles, does strength have any effect, or do we just follow the lines,
So-
the arrows?
So for the saddles, that's a good question. Do the strengths have any effect? The answer is yes, but it's negligible in your handlings. So, in your hand drawings, it'll be negligible because they'll all have this form. But if it's really, really strong for one of them, it'll slap to that line a little bit faster, but it's the subtlety will not be apparent in your hand drawing. Does that make sense? But
Okay,
here, it will.
gotcha.
So for here, you don't have to worry about it. Just draw the swoops in between and it's fine. For here, this matters because there is curvature to it and I want you to capture the curvature. So let me go ahead and put this one in. So this is -2, -2. -1. All right, so and notice if you just click right here, you give this. You can look at this. We're not going to get into that, so don't do more of that for now. I've done something wrong. Hi. Boop, boop. What happened here? -2. These were -2 and -2 a second ago. All right, here we go. Drawing our eigenlines. Bam. Those are eigenlines as we have drawn, right? And notice which way the swoops are going. Boop, boop. Within the direction of the eigenline for λ2. So this one. So they're more in that direction. Does everyone see how the curvature and how to draw that in? There we go. All right. So with all this said, before we go on to the next point, let's talk about the project. Because this is the perfect time to talk about the project. It's not 181. This is not what I wanted. I mean, I can get to what I want, but let me show it to you in the modules. I don't spend an inordinate amount of time making these for fun. Yeah. All right. Project. Here we go. Boop. All right. So what is your project? So this is due April 18th, Sunday. So you need to describe 10 different 2x2 systems with the following. You have to give it some sort of name. So do we have some names associated to these? Yeah. I call this a sink, right? I call this a saddle, and we call this one, oops, now I'm in complex solution. We called the one I threw away. I threw it away. A source, right? And so you're going to have to state what eigenvalues cause it to be this way. So sinks are going to have 2 negative eigenvalues because then all the lines will go in. So let me go back. Let me go back to, hold on, let me open that up. I should have put this, thinking about this, I should have put this at the other end. They modified, yeah, I want today's stuff.
Professor, what was the third one called?
Source.
Source.
Yeah, hold on. I'll open it up right now. Bing. Here we go. So here, if I have one negative and one positive lambda, we call this a saddle. And we drew a picture for it not that long ago, right? If I have some λ1 and some λ2 and they're not equal to each other and one's more negative, right? I have here a sink and it looks like this. And if I have a lambda and if I have 2 positive lambdas, I call this a source, right? And so if I have a negative and a positive, it's a saddle. If I have two negatives, it's a sink. And if I have 2 positive, we call this a source. Okay, so we want the name. So we call this a saddle, sink, and source. And so here, let me just show you kind of briefly what in this. All right, so here, I just want you to create some sort of table, right? Some sort of table, right? And in the table, and I do want it typed. I do want like these, the projects I want typed, everything else can be by hand, but these I do want typed because I want you to force you to use the computer here and kind of get used to writing this notation. So here, we're going to call this a sink, right? What eigenvalues make it? Lambda 1 is less than lambda 2, which is less than 0. And then you're going to make up some sample matrix, right? Pick up a sample matrix. If you work in groups, just make up multiple sample matrix, okay? I picked something relatively beyond simple, right? Because I know this is going to equal what I want. So pick some sample matrix. So just kind of pick something. Solve your sample matrix. So solve the sample matrix eigenvalues and eigenvectors, right? So in this case, it's lambda 1, lambda 2, and these are this. And then draw the face portraits in whatever you want to use. I suggest just using this, right? So here, this is another example I could have used, right? It could be -2, 2, 1, -3, and then here I get this, and this is what it looks like, right? I mean, if this was 4 and 4, and you know, just kind of futz with it, right? Here's another system, right? This is also a sink, right? My eigenvalue is a little bit funny, but that's fine, right? And here I still get the same. And then here you can just, you know, just do a screen capture, just say, hi, I want this. Boop. And then presto, right? There's a way to do this in Windows too. So I'm just grab it and post it in. Okay. And so you're going to find 10 of them. We're going to go over 9 in class. You should be able to discern another one. I'll give you a hint. It involves zeros, right? It involves zeros. So you should discern another one. Okay. And so that's what you're going to do for that. This is due Sunday. I'd probably do it way earlier than that, but this is due Sunday. Any questions on this?